Okay, so let's look at the next couple sections here. 1.17 says that there's 2 ports in the same switch, but we don't want them to communicate directly between each other. Do not use private VLANs to accomplish this. So obviously you could use private VLANs then to solve this type of problem. Specifically in this case, it's talking about just the port protection feature, which is the switch port protected command. So again, like we were talking about before, for these type of features, you just need to spend some time reading through the documentation so you know what's available. For the switching, specifically when you start at the main product page, we would go to products, switches, LAN switches for access, 3560, configuration guides, then this would be under port-based traffic control. So the storm control, port protection, port blocking, port security are also under here. So minor features of these configurations, again, you don't need to memorize as long as you know these documents are here. Like in the case of port security, you see this table that shows you what are the different methods and what do they do. So as long as you know there are these different violation modes, you don't need to memorize exactly what happens here. You can always just come back in and reference this. Same is true for like the port protection. So the configuration for this, again, is just one command, switch port protected. Then port blocking, switch port block multicast or unicast. This is going to stop it from doing MAC address learning on the interface by flooding your unknown frames out the link. And essentially what these two configurations are used for together is to make sure that, let's say you have a shared hosting environment where you have one web server and a second one that are on the same LAN segment. You typically wouldn't want one of them directly talking to the other one. So let's say this first server gets compromised, then there's no way that it can send traffic to the second one. Okay, the other thing it's protecting against is this attack that's known as the MAC OF attack, MAC-OFF, that's used to flood a switched LAN with random MAC addresses. And what this attack is designed to do is to fill up the CAM table of the switch, so it runs out of memory, and then it treats all of the frames like broadcasts. So the attacker just sends tons and tons of unknown frames. The switch runs out of memory, and then everyone on that VLAN, that particular port starts receiving the traffic. So it basically turns the switch into a hub. So running port security would fix this. Also, the port protection with these two commands would stop you from flooding the unknown frames out the interface. But typically, these three commands are going to be used together. You could use this one without the port protection or vice versa, but normally you would want all three. Then again, 1.18, this is talking about the storm control feature. You could technically do this also with policing under the quality of service, but the problem is you can't match on packets per second. So for policing under a service policy, you can match on a bit per second value or a percentage of the link, but not a packet per second value, which is what this one is talking about. So just if you go above that rate, then you are going to start dropping the broadcasts. 1.19 is talking about the remote span feature, where we're trying to essentially redirect traffic from a specific segment. So it says any traffic that router 4 receives, we want to redirect it to this particular port. But the issue here is that router 4's port is not physically connected to this switch 3, so we need to redirect it to an intermediary device, where we're saying that when traffic goes to router 4, make a copy of this on VLAN 999 Then on the other end, when it comes in 999, we're going to send it out that interface. So then just based on how you configure your span sessions, you can redirect different portions of the network to like your packet sniffer or to IDS.
Can you scroll to the right a little and finish that bottom command?
This one here is a hardware limitation of some of the platforms. 3560 doesn't need this command. So what this basically means is that the span process is using the ASIC of this port in order to loop the frame back. But if you use this command, it means that this port has to be unused then.
Yeah.
In the question it asks for traffic that R4 receives, so we set the span to TX, but technically there you could do both, right?
You could do both.
Because it will still capture it.
It's going to capture both of them, right? Yeah. You could also say, listen for it on the VLAN. The VLAN would be both directions. So if we look at the diagram here, it's talking about traffic that's going between BB3 and router 4, where technically, since there's only 2 hosts, I could say watch the traffic as it comes in from BB3, watch it as it goes out to 4, watch it both directions on 4, both directions on BB3, or watch it on the VLAN itself. So technically, any of them are correct. But the key here is that you need to look at what's the physical transit path, where when, so this is going out to the rest of the network, when router 4 is receiving the packets, from the switch's perspective, this is what's being transmitted. So for these type of miscellaneous features, like I mentioned, the documentation is going to be a good resource for this. Also make sure you spend some time going through the Volume 1 workbook for the switching section, and you'll see some examples of these type of miscellaneous tasks. So under Routing and Switching Workbooks, Volume 1, and even if you don't have time to go through all of these labs, you can use this kind of along with your checklist to make sure that you've hit all of these topics. So some of the miscellaneous stuff like the multiple spanning tree, there's really not too much of a configuration issue with this when you compare it to the regular spanning tree configuration. So the main difference is that when we look at the, let's look at the solutions for some of these. It says we're running multiple spanning tree with these mappings for the VLANs. Syntax-wise, you're simply saying that instead of one VLAN per spanning tree instance, you're just grouping them together. So I have 3 instances that are made up of these 3 groupings of VLANs. Then the rest of the commands are going to just use spanning tree MST instead of spanning tree VLAN. There's also a scenario that I go through in the Advanced Technologies class that is kind of a corner case design for this, where you have multiple regions of MST. And essentially what this is designed to do is that you have a giant layer 2 switch network for some reason. And between these regions, we want them to look as if they're independent clouds of spanning tree. So inside these individual clouds, we're going to have a root bridge, just like a normal election. But then between each other, the entire cloud looks like one switch. So one of these inter-region links is going to be the root port, where maybe this is the regional route for everybody. So this is the root port, that's the root port, this would be the designated ports. Then one of these is going to be designated and one of these is going to be in the blocking state. Really the only issue you can get into with this design is if you're trying to do backwards compatibility with either the single common spanning tree or Cisco's per VLAN spanning tree, where if this region goes down to PVST or the legacy common spanning tree, the design restriction is that the root bridge cannot be in this cloud. The root bridge for everyone has to be in one of these three. Otherwise, you'll see an inconsistency, because essentially out this link, there's a type of spoofing that it does so that the per VLAN spanning tree doesn't need to know about the instance mappings, or the same as the common spanning tree. But as long as the root bridge is somewhere up here, then this is going to be just a normal root port that's facing upstream towards them. Peter actually did some really detailed write-ups on this on the blog.
So how often do you update your workbooks? Is it a yearly thing, or like if there's an? Because I've provided some.
Like bug fix type stuff?
Yeah.
Bug fixes we kind of do on the fly. The problem is the content is too big to keep track of, to do any like change control on it.
Yeah.
So a lot of times we'll fix minor things and then release a new version of it. And then unless you actually download that newest PDF, then, because I mean, if you look at the file, it's 2,000 pages, 2,600 pages. So it's kind of hard for us to manage it at this point. Yeah, so this multiple spanning tree, there's you can see he's got a table of contents for it. It's so big, but it goes over these different types of topology designs. Most of this stuff is going to be outside the scope of the exam. It's more like a large scale layer 2 design issue, especially when you look at these inter-region configurations. So it's good for the theory behind this, but syntax-wise, it's fairly simple to actually do this configuration. Okay, some of the other miscellaneous things like pretty much everything up to section 1.17 is the type of stuff that we talked about yesterday. So this would be considered the core of the switching. Then beyond that is spanning tree features, spanning tree convergence, tuning, the equivalence of this in a multiple spanning tree. Then the security stuff, port protection, storm control, MAC address aging time, static entry. So if you wanted to null route a layer 2 address, you could put a static MAC address entry and then point it to null 0. So kind of just like a black hole route on the routers, but you're doing it for the CAM table. Then flex links. This is like a lightweight version of spanning tree. It's basically the backup interface command for switches, where I'm saying that if this port channel goes down, then fast Ethernet 16 is going to be used instead. Then there's some minor optimizations of this, like the convergence. But this would then disable spanning tree on the links. So if you have some very simple layer 2 design where maybe you just have 2 uplinks, you don't necessarily need 20 instances of spanning tree in order to keep track of that. I'll just say if one link goes down, then just automatically start forwarding over the other one. Fallback bridging, again, this is kind of another corner case here, that if you have non-IP protocols, the switch can bridge them between different routed domains. Like we have a routed interface here, and then we have a VLAN interface. They're both in the same bridge group, which is a VLAN bridge. So if you had NetBIOS or IPX, like legacy applications, you could bridge them between the different layer 3 interfaces. Private VLANs, you definitely want to take a look at this one. The syntax can get a little bit complicated for this, but the logic of this is pretty straightforward, that we essentially have a primary VLAN that's made up of these different types of secondary VLANs. These secondary VLANs can be two different types. They can be communities, or they can be isolated. Then of the primary VLAN, there's going to be a promiscuous port. That's probably spelled wrong. That goes to the router. So the typical design for this is like shared hosting or like data center environment, where you don't want your servers to talk to everyone else on the network, but you want to make sure it can get to the default gateway. So let's say that you have customer A that has two servers, A1 and A2, customer B that has B1 and B2, and then customers C and D that only have one server each. Now we want everyone to be able to talk to the router so you can actually route the traffic out to the rest of the IP network. But I want to group these together so that A1 and A2 can talk to each other plus the router. Then B1 and B2 can talk to each other plus the router. C1 can talk to no one except the router. And then the same for D1. It can talk to no one but the router. So when you do the VLAN assignments, you would have a community VLAN for A1 and A2, a different community VLAN for B1 and B2, then C and D, these would be in the isolated VLAN. Then all of those, the communities and the isolated, they can all talk to the promiscuous port.
Is that port-based or VLAN-based?
It's VLAN-based.
So
You can span between multiple switches.
and you could put those servers, say, on a VMware machine and then assign the community VLANs appropriately.
Right. So you can, let's say you're doing layer 2 trunking to the VMware machine,
Yep.
when the traffic comes in, it's already going to be .1Q tagged. So then the switch will know how the traffic is supposed to be separated. Because if you're trying to get one virtual machine to route to another one, so you have the overall physical box, but then it's made up of the actual like the instances, the hosts. So if I have A1 and A2 and B1 and B2, assuming you're not like doing the like a binding internally, they would have to send their traffic out to the hypervisor. Then it actually goes to the switch, and then the traffic loops back around. This is what the switch would prevent for you, or you would be able to control it however you want. So we say that what's the primary VLAN to begin with? Okay, in this case, it's 100. 100 is made up of a couple different secondary VLANs, 1000, 2000, and 3000. 1000 and 2000, I said this is a community. The other one is isolated. The promiscuous port typically would have all of the VLANs assigned. You could do some sort of subset of this if you have some real complicated network, but normally you want everyone to be able to get to the promiscuous port, who's the router typically. So then this association here is basically saying my primary VLAN is 100, but the port is then assigned to the secondary VLAN 1000. So this is putting them in the community. Then this one's in 2000. So these two ports wouldn't be able to talk to each other, but they would be able to talk to this one. Then it can span multiple switches. On the other switch is doing the same thing. So you have to do these mappings between them. Notice also that it's in VTP transparent mode, because you cannot advertise these VLANs unless you're running VTP version 3. And most of the switch versions don't support that yet. Only the latest code on like 6500 supports VTP version 3. So for this, definitely I would recommend to use the documentation, because the logic you can understand, but if you mess up the syntax just a little bit, then it's not going to work the way that you want to. Okay, let's see if there's anything else. Some of the security stuff we'll talk about later, like .Winx authentication. The voice stuff, that's pretty straightforward, just the voice VLANs. You could use that template that I showed before, and you could pretty much figure out the configuration from that. DHCP features IP source guard and dynamic ARP inspection. These would be for preventing those layer 2 spoofing attacks. IGMP snooping and multicast VLAN registration. This is typically if you're trying to do IPTV at layer 2 on the LAN, where a port can join a particular multicast VLAN and then receive its normal unicast traffic, but then also multicast traffic based on a different layer 2 segment. Then there is one other feature here I wanted to talk about. Let's go to the regular 3560. That was the wrong platform. Switches, LAN access 3560, configuration guides. The FlexLinks feature. Link local discovery protocol. This is basically an open standard version of CDP that you could turn on. Access lists we'll talk about in security with like VLAN access lists. And most of the other stuff is pretty standard. I thought there was an interface feature here that's for link tracking. I'll come back and look at this while we're on break. But again, if you just sit down and spend the time, I mean, to really read through the whole thing is probably going to take you a week out of your preparation. But then once you know that the features are there, you can always fall back to the documentation. But again, the big key is that if you didn't even know what is dynamic ARP inspection, then based on a question like this in the exam, you're going to have no idea where even to look in the documentation. Because the question is probably not going to say, configure dynamic ARP inspection on switch 1 to do this. It's going to give you some description of what the problem is and then just say solve it. And you'd have to know what's the design for that type of feature.
Would you recommend reading the entire thing cover to cover, or just going through the kind of the introduction to the technology?
Probably at least just the, let's say like DAT1Q tunneling. Read the understanding sections. So a lot of the stuff below this, the configuration and the verification, most of this is pretty redundant. It's pretty simple just to look at whatever the configuration guide says and like let's say configuring like these DHCP features. If you look at configuring this, they're just going to give you that bulleted list. It's pretty easy in the exam time to follow this along. But if you read just the understanding section, this is basically going to tell you what's the design of the feature, what's the problem that it's trying to solve. So then once you know that that's there, then you could just move on. Okay, any other questions in anything that's Ethernet related?
So basically, in the exam, the question is between the layer 2 in 30 minutes, 1 hour maximum?
It depends on how many questions there are related to it. I mean, you could potentially get a security or a switching section that's like 6 points or something like that, and most of the weighting is on routing. So you don't necessarily need to say, like, by lunch, I'm going to make sure I finish IGP, or, you know, this is the time goal. You can only figure that out once you actually see the format of the exam and what the layout is. But the first goal for Ethernet would always be what? Just the basic connectivity. If you can get basic connectivity working, then you can skip around through all the rest of the sections and not worry about it. So if you got something like this, let's say like the remote span, and you're not 100% sure how the configuration works, I would skip this and then come back to it later in the day. But if you didn't configure the VLANs, then none of the other stuff is going to work. So the same would be true of the WAN technologies, mainly frame relay. So there's a couple different variations it's talking about here. Make sure you know the differences between how the main interface works versus the sub-interfaces, when you need to use static mappings versus dynamic mappings, or when you don't need them, and then also how this is going to affect the layer 3 network. Like in this case here, it says routers 3, 4, and 5 are running frame relay. Router 3 is the hub. Use a sub-interface on router 5. Do not use any static layer 3 to layer 2 mapping commands on router 3. So really, they're unrelated requirements here. But how you choose to actually build this network is then going to affect later what's running on top of it. Maybe OSPF or eEdgeRP or multicast routing. If router 3 here, it's using the main interface, it says don't use static mappings, which means what? That we're going to be doing inverse ARP for the spokes. Now the spokes cannot do inverse ARP though, because they wouldn't be able to map each other. Inverse ARP is only for a connected neighbor at layer 2. So if they're using the main interface, it means that they would have to have frame relay map commands. If they're using a sub-interface, and the sub-interface is multi-point, then the same features that apply to the main interface are going to apply to the multi-point sub-interface. We'd either need the static mappings or we would need inverse ARP. If we use a point-to-point sub-interface, that's going to allow us to do what? Just assign the PVC number, and then you don't have to worry about the mappings. Because it has to do with a layer 3 to layer 2 resolution, where when the routing process switches the packet to the interface needs to know what's the layer 2 address that I need to put inside of the frame. And that's what the frame relay mapping is doing. It's basically the equivalent of, like on Ethernet, looking at the show ARP. So in this case, for switch 1, it knows that if it's sending a frame towards this next hop, and it doesn't necessarily have to be towards this as the final destination. This is just the next router in the path. It knows that in the Ethernet header, it needs to use this address. The same would be true of frame relay. When we look at router 3 and look at the show frame relay map, it knows that if I'm sending a packet towards this next hop, so it doesn't necessarily have to be to that as the final destination, it's just the next hop in the path, then it needs to use circuit number 305. But if it doesn't have this association, then when you actually build the layer 2 packet, the encapsulation is going to fail, and it's not going to know where to actually send the frame. So here it looks like we have a dynamic mapping to to router 5, but not to router 4. So let's look at this on all of them. Let's say show frame relay map. 4 has static mappings to 3 and 5. Five has static mappings to 3 and 4. 3 has a dynamic mapping to 5, but it doesn't have a dynamic mapping to 4. So this isn't really a configuration issue here. This is like what Brian was talking about yesterday. If you had the choice of using a static configuration versus a dynamic one, you know 100% of the time the static one is always going to work. But there's something now wrong with the order of operations for frame relay, that if I look at the debug frame relay packets and debug IP packets, I should be able to send a frame to router 5. And we can see that the layer 2 process knows that I'm supposed to be using circuit number 305 when I send packets outbound. But if I try to send this to router 4, when the packet actually gets to the interface level, encapsulation is failing because it doesn't know how to resolve the layer 2 address. So anytime you see this message either in a layer 2 debug or the layer 3 IP packet debug, encapsulation failed, it means for some reason it couldn't build the layer 2 frame. And usually it has to do with the fact that it doesn't know the layer 2 address of the neighbor. Also, if you look at this show frame relay map and you see these mappings that go to 0, there's only one way to solve this. You need to write and reload. The reason why is that it has to do with auto install over frame relay. That when the router boots and it does not have a config, it tries to do boot P over the interface and basically get an address through DHCP and then try to automatically download its configuration. So if you save and reload, next time the router boots, and since it already has a configuration saved, it's not going to try to run auto install. It's the only way to get it off. So let's see, when router 3 eventually reboots, we want to see that it has dynamic mappings both to 4 and to 5. Now, it also told us on router 5 to use a subinterface, but it didn't say what type. So we would have the choice here either to use a point-to-point or a multi-point subinterface. If we used multi-point, it means that we either need a static mapping, or we could use inverse ARP by simply assigning the PVC to that interface. So if I remove this statement and I replaced it with frame relay interface delc 503, as long as the IP address is on there, it means that it's going to try to do inverse ARP for that circuit. If this was a point-to-point subinterface, then the only thing it needs is just the delc number. But now later when we're running IGP over the interface, for this particular design we are running OSPF, and I want to say it's area 0 here. So how we configure the frame relay is then going to affect how OSPF is going to behave, because there's different default OSPF network types depending on the underlying interface type. Like a fast Ethernet or a gig Ethernet, that's going to run as network type broadcast. A multi-point WAN interface, like frame relay, ATM, ISDN, those are going to run as non-broadcast. A point-to-point WAN interface, like HDLC, PPP, point-to-point frame relay, point-to-point ATM, those run as network type point-to-point. But the problem is there's compatibility issues between the network types if they don't agree. So if I'm running network type point-to-point and you're running network type broadcast, we cannot be adjacent because of why? Because of the DR election. And the reason why is that when you actually do the SPF calculation, the broadcast and non-broadcast network types use LSA number 2 to do a recursive lookup in the database, but point-to-multipoint or point-to-point, they don't use that. So you end up in this inconsistency where if I'm point-to-point, I don't know how to use LSA2. And if you're broadcast, you need that, so then the calculation fails. Okay, you might actually see that the adjacency comes up, or more accurately, the neighbor relationship comes up, but they're not really fully adjacent because they don't exchange the database. So if you look in the routing table, none of the routes are going to get installed. You have to make sure that they're compatible. So in general, you can just group them together based on, do they support the DR or do they not? Where the ones that do support the DR and BDR election are what? Broadcast and what? And non-broadcast. The ones that do not support the DR-BDR election are all the other ones. So point-to-point, point-to-multipoint, point-to-multipoint, non-broadcast, and then technically loopback, and then also virtual link. So virtual link is always a point-to-point link. This doesn't have a DR election. So it means for the point of adjacency, you can have combinations between these in order to get the neighbors up. You could also have combinations of these. So broadcast to broadcast, non-broadcast to non-broadcast, broadcast to non-broadcast, as long as the other parameters of the adjacency match. So like the timers, the authentication, the area number. Same is going to be true with these three. So you could technically have any combination of these three together as long as the other variables are agreed upon. Now, what else is this going to affect besides just the election process and whether we're using that LSA2 or not? Okay, the timers would be one, so they have different default timers. What else would be different, let's say, between non-broadcast and point-to-multipoint? Okay, that would be another one. So when we're actually doing the configuration, if we were using non-broadcast, router 3 would need neighbor statements for the spokes because it tells it where to send the unicast updates. So that's another one, that the neighbor statement is for your unicast updates. For the other network types, it's going to use multicast updates. But let's say we're running non-broadcast versus point-to-multipoint here. How is it going to affect the actual layer 3 routing over the network? Let's say we have a host A down here that's trying to reach host B on VLAN 5. When 4 gets this packet in, if the network type is non-broadcast, what does it see the next hop value as? Let's think about it this way. Let's say that we had an Ethernet segment that we have 6 different routers on. So they're all on the same LAN. They're running OSPF. They're running the default network broadcast. This means that someone is going to be elected the DR. Someone is going to be elected the BDR. So this means that if router 4 has host A and 6 has host B, if we want to send updates about these links, we're going to send the copy to the DR. The DR is then going to send it back down to everyone else. When we actually go to send the traffic, though, what happens with the traffic flow between A and B? It goes from A to 4. Where does 4 send it? 4 sends it directly to 6. It doesn't send it to the DR. So this means that when the DR gets the link state update and it forwards it on, it's not changing what? It's not changing the next hop value. So it's preserving the next hop because the DR figures that if you guys are on the same layer 2 segment, you already have direct connectivity to each other. You don't have to go to me first. But the problem in designs like this is that the neighbors really are not on the same layer 2 network. It's a collection of point-to-point layer 2 networks. Now, frame relay design, this is really a legacy application of this. But in new network designs, this is the same type of problem where you would see over like a DMVPN network, if you're doing a multi-point GRE tunnel, or if you're doing any type of VPLS or OTV, where you're basically simulating a broadcast network over IP, where it's not really a shared layer 2 network between all the devices. It's an emulation of point-to-point layer 2 segments. So the problem here with non-broadcast is that when router 4 is trying to get the packet to B, it needs to do a next hop lookup on 5's address. And if router 4 doesn't know that this address .5 is reachable out this circuit, then the encapsulation is going to fail. So it means that 4 would need a frame relay mapping for this address. So it's not really OSPF's fault per se, it's that OSPF doesn't know that router 4 and 5 are not on the same layer 2 network. But the way that you fix this is by running it as point-to-multipoint. So in point to multipoint, 3 and 4 would be adjacent, and 3 and 5 would be adjacent. Based on the fact that 4 and 5 do not form adjacency, they figure that they're not on the same layer 2 network. So even though they're on the same subnet, they know that they cannot exchange frames directly. Because if I could exchange frames directly, I would be receiving multicasts in from them already. So now when A is trying to get to B, when 4 does the lookup here, it's not doing it on 5's address, it's doing it on 3's address. So the point here is that you need to look at the combination of both of the designs together. If you're running OSPF over the NVMe network, then you need to think about, does everyone have layer 2 connectivity everywhere? Now, if this was a full mesh, it would be a different issue. If I had PVC 405 and 504, then I could run just network type broadcast, send the multicasts out to all of the circuits, and then eventually all of the neighbors are going to figure out who they are. But the problem of a design like this is that with broadcast or a non-broadcast network type, we're going to have what on the segment again? We're going to have the DR election. The DR is used to propagate the updates. But what happens if you don't have layer 2 connectivity to the DR? Then the updates are going to get segmented. So let's say theoretically that router 3 is the DR, but I have a full mesh of circuits. If the circuit between 4 and 3 goes down, I technically can still reach 3, I just have to route my traffic this way. But the problem is now I cannot get a link state update from 4 to 3 because 5 is not going to forward that on. So in complex layer 2 designs like this, it's a bad idea to run network type broadcast or non-broadcast. You would want to run point to multipoint, so then regardless of what the underlying layer 2 network looks like, as long as there's some path between the routers, the network can self-heal itself around any type of failure. So our next one, 2.2, says between routers 1, 2, and 3, we're running frame relay. Use subinterfaces on router 1 and 3. Router 2 should perform dynamic layer 3 to layer 2 address resolution. So router 2 is doing what? Router 2 is going to be doing inverse ARP. 1 and 3 are going to be doing what? Well, it doesn't really say. It says use subinterfaces, but it doesn't say, can I use point-to-point? Can I use multi-point with static mappings? Can I use multi-point with dynamic mappings? So then we have to figure out what's the appropriate design to use. Okay, it's not really that one is better than the other. Probably the easiest one to configure would be to do what on router 1 and 3? Is to put just a point-to-point subinterface here, because then I could just assign the circuit, and I don't need to worry about any of the layer 3 to layer 2 mappings. For router 2, we're going to need 2 different subinterfaces, one that goes to router 3, one that goes to router 1. If I want to use dynamic mappings on these, what does router 2 need to do on these subinterfaces? We need to move the circuits from the main interface to the subinterface. If we look at the show frame relay PVC, when you learn the circuits from LMI, from the frame relay network, normally they're going to land on the main interface. If I want to move them to the subinterface, there's 2 ways I could do this. Either with the frame relay interface DELSI command or with the frame relay map command. So both of them are assigning the circuit, but one of them is doing a static mapping. One of them doesn't have anything to do with the mappings. This is just saying assign the circuit to the interface. If the circuit is on there, we're running IP and the interface is multi-point, it means that inverse ARP is going to be enabled on this circuit. So if we look at the show framing the map, we should ideally see that router 2 is going to get dynamic mappings for 1 and for 3. But again, this wouldn't be really our preferred design. So the questions are worded this way just to show you that you can do it in these different types of variations. But if you were to choose how the network was built, you would run point-to-point subinterfaces on all of these. And you would change this network so there's not a disconnect between the layer 3 network and the layer 2 network. Because the problem is that all of these 3 neighbors are on the same subnet, but they're not really part of the same network, because there's no layer 2 connection between 4 and 5. So if I was to say that this is not one subnet, I have a subnet 34 and I have a subnet 35, then they're obviously going to know that they're on different networks because they have to route to get to each other. We'll also see that when we get to multicast, this underlying layer 2 design is going to affect a lot of things with the PIM behavior over the link. Yes?
Left there, but they're really not. If I was to actually, if I turn broadcast on for both of the actual DLCs on each of the, on round 4 and round 5, would I have to actually turn priority 0 to keep it from becoming DR? Or trying to?
Yes, you would. Okay, so the question is, if we were running OSPF broadcast or OSPF non-broadcast, we need to make sure that router 3 is the DR, because why? Because the other two don't have a layer 2 connection to each other. So there's no way for them to directly exchange link state updates. It has to go to the DR first, and then the DR is going to send it down. So router 3 has to be the DR. The problem is that most of the time when you're learning first about OSPF, they say that what's true about the DR election. That once the DR is elected, what's going to happen?
It's only going to, if it goes down, it will never be DR again, unless BDR gets promoted, then just a re-election.
Why not, though? So if I'm the DR and I go down and then I come back, why don't I immediately become the DR again?
Because the BDR is already taken over.
Because there's no preemption in the election. So it means that even if my priority is better than yours, I'm not supposed to take over for the election. But if you read this specification, that's not really what it says. It says that when you first come onto the link, you go into the wait state, which means that you're going to wait for the dead interval to expire before you start sending your hellos on the interface. So the idea behind this is that if I'm joining a LAN segment, that I'm going to join and I'm going to start listening for everyone else's updates first. So I'm already going to know who the DR is. So if the DR is already elected, I'm not going to try to tell anyone else that I'm the designated router. But if for some reason the wait state expires and I don't already hear about the DR, I immediately elect myself as the DR and then start advertising that out to everyone else. So in reality, the way that it happens is that the DR is elected based on the order that the OSPF process loads. Whoever loads the process first is always going to be the DR. Okay, unless their priority is 0. Priority 0 says don't participate in the election. And this is the reason why in this design, you have to set 4 and 5's priority to 0, because there's no way that we can predict what the order of the processes are going to load. So if router 3 is under high CPU load for some reason, 5 could elect itself the DR, and then router 4 is never going to be able to send or receive any updates. So we do this on the interfaces here. I would want to say The IP OSPF priority is 0. So then it doesn't matter what router 3's priority is, as long as it's not 0, it's automatically the one that's going to be elected the designated router. And it's kind of interesting. You can see this in action, that if you had this type of design here, where we have a bunch of routers on the LAN, let's say that one has a priority of 255, and it's the one that's elected the designated router. And let's also say that this whole segment is like VLAN 10. Now, if I connect router 4 and I assign this to VLAN 20, so it means router 4 right now, it doesn't have connectivity to the rest of the devices. When its OSPF process loads, it doesn't hear any of the other routers, so it does what? It elects itself as the DR. Okay, at this point, the wait timer has expired because it was first waiting to see is anyone else the DR. It didn't hear any of their updates, so it automatically elects itself. Now, if I change the VLAN assignment from 20 to 10, there's going to be two possible results. If router 4 now sends a hello packet before 1 does, 4 actually will preempt 1. Because the RFC doesn't say there's no preemption. The RFC says you're supposed to wait first. And the wait timer is automatically supposed to figure that out, that if someone is already elected and I hear them, I'm not going to elect myself. But the problem is if there's some strange behavior in the order that the process loads, you actually can take over someone else's DR state.
Will router 1 in that case realize that it's no longer the DR?
Yes. Because if you receive an update in that says someone else is the DR, you always trust what their update says.
And can you clear OSPF process?
You can, and that would reset it. But again, it depends on how fast the process loads. So if router 4, let's say, is just some fast CPU and the other ones are older routers, if you clear all of them at the same time, whoever converges first is always going to be the DR. So you can keep clearing them over and over, and you'll see that the role is going to change depending on the order that it actually runs in.
Probably just shut the interface and then clear and then bring up the other ones.
Right, yeah.
Later.
But the thing is, in a true broadcast design like this, it doesn't really matter who the DR is, because the DR is just used for the control plane. It doesn't have anything to do with the actual forwarding of the traffic.
Yeah, and that's fair.
And it's not really that CPU intensive anymore to run the SPF algorithm. So if router 1 is an 1800 and the rest of these are like, whatever, 7200 VXRs, it doesn't really matter if router 1 is the DR because it's not used for the transit of traffic. It's just used to do the LSA exchange. Then if I have traffic that's going between A and B, it's not going to use that router. It's going to go this way. Mm-hmm.
It would kick, so say 4 was DR and 1 was DR. 4 would tell 1 to stop being DR? It would tell it that?
It won't tell it to stop being the DR. 4 would just say that I'm the designated router, and then router 1 would automatically accept that. So let's look at it this way. Let's take a look at the topology. Let's try this between, let's say, router 3 and switch 3. Okay, router 3 here is supposed to be 173.18.39.3. And switch 3 is VLAN 39 is 173.18.39.9. And then that layer 2 port that goes to router 3, switch port access VLAN 39. So router 3 should be on the same segment now as switch 3. Okay, let's take a quick, just 5-minute break here. I need to double check this topology and see what's going on. Then I'll show this example real quick. Then we'll break for lunch and to keep working on the rest of the labs. And then later this afternoon, we'll start to review some of the next section, the IGP.
Brian, just have one question regarding the frame relay sub-interface. It doesn't really say, point-to-point. We use point-to-point or point-to-multipoint. What should I use?
You'd have to look at the IGP design first. So if it's going to affect OSPF or if it's going to affect multicast or any of the other routing protocols, usually a point-to-point subinterface is the best design choice. But if both of them if it's running on both sides, if one is point-to-point and the other one is multi-point, it's going to work from an actual layer 2 point of view, but then OSPF would have different defaults on the interface. So if you're configuring frame relay and it doesn't say what you're supposed to do or what you're not supposed to do, but then in OSPF later it says don't use the OSPF network statement or make sure this is running as this network type, then you might not be able to get both sections to work at the same time. So you could get the first section correct while losing the points for the second one or the other way around. So you need to make sure that the design is always going to match so that you can get credit for both sections.